In Stoichiometry 1, we looked at going from moles of one thing to moles of another based on the mole relationships or the mole ratio that we knew from a balanced chemical equation. Now, really, that's not very practical. It was easy and a good intro for the first round, but we don't measure in moles. When we put something on a balance and we read off the number, we don't get number of moles, we get number of grams. So just going from moles to moles doesn't really help us in the practical sense. So we need to go from grams of something to grams of something else. That we can measure grams. However, we can't go from grams of compound A to grams of compound B. They might be different because different compounds have different molar masses. So we have to go from grams of A to moles of A to moles of B to grams of B. So this part here in the middle is what we did before. We're just tacking on the very beginning and the very end, going from grams to moles, and then from moles back to grams. So let's look at a couple of examples. So our first example we're going to walk through together. So example 1 says, you heat sodium bicarbonate to produce carbon dioxide, water, and sodium carbonate. If you start with 3.1 grams of sodium bicarbonate, how many grams of water will you produce? It's a very practical question. We did this in lab. So how much water did you actually produce? The first thing that you want to do is you need to write the equation and you need to make sure that it's balanced. So sodium bicarbonate is NaHCO3. Sodium carbonate is Na2CO3. Carbon dioxide is CO2 and water is H2O. So there are our formulas. This one's already balanced because I put the 2 out here, so that gives us 2 sodiums on each side. Here are 2 carbons, 1, 2 carbons, 2 hydrogens, 1, 2 hydrogens, 2 times 3, 6 oxygens, 3, 4, 5, 6. So everything's coming back into play here. You have to be able to write your formulas correctly, and you need to make sure that your reactions are balanced. Otherwise, all your numbers are going to come out wrong. So we have our equation, and it's balanced. We're good to move on to the next step. So I originally wrote step 1 in blue, so here it is in blue again, so you know where that came from. Step 2 is to set up our BCA table, our before, change, after table. Same purposes as we had in Stoichiometry 1, and our numbers are still going to go in as moles, but we have an additional step. So here's our BCA. We know that we're going to fill out our before, our change, and our after. Step 3 is to actually put those numbers in. Now, you can't put grams into a BCA table. You could, but when you go to do all your conversions, things would come out weird. So you have to make sure that you're in moles. To do that, we originally had 3.1 grams of sodium bicarbonate. That's what we have from our question, our original problem. The molar mass of sodium bicarbonate is 84.01 grams in 1 mole. So if we do our grams to mole conversion, we end up with 0.037 moles of sodium bicarbonate. So that's how many moles we're starting with. So that goes right up here. And we know that we don't have any sodium carbonate, no carbon dioxide, and no water originally. So all of those are zeros. We know that we're going to use up all of our sodium bicarbonate, or we're going to assume that we use up all of our sodium bicarbonate. I ignored these for right now, but that's simply because we weren't calculating them, and I only looked at the water. The ratio between sodium bicarbonate and water is 2 to 1. So if we set up our problem down here, so we have 0.037 moles of sodium bicarbonate. The ratio of water to sodium bicarbonate is 1 to 2. So we know that we're going to have 0.0185 moles of water. We're going to have half as much water produced as we had sodium bicarbonate consumed. So we're going to add 0.08185 moles. So we're going to end up with 0.0185 moles of water at the end. Now that's not what our question asked. If we were doing Stoichiometry 1 type problems, mole to mole, we'd be good, we'd be done. But we can't measure moles. We can, however, measure grams, and that's what our problem asks. So our very last step is to convert back to our desired units. So in this case, we wanted grams of water, so we need to go from our moles of water to our grams. Here's our moles from our step 3, when we calculated using the BCA table. We know that water has 18.01 grams in 1 mole, so this is a mole to mass conversion. And you end up with 0.33 grams of water. And that's it. So really, fundamentally, it's no different than our stoichiometry 1 type problems, except that we have an additional piece at the beginning and we have an additional piece at the end. We have to get from our starting units to moles. Then we do all of our in-the-middle stuff using the reactions, using the mole ratios in mole units. And then we convert back to whatever units we need at the end, whether that be grams, we can use density to get from grams, then to volume, whatever the question asks. This example I want you to try on your own. So you can see from this board, we've done step 1, the equation and balance, but let's look at the question first. You decompose 100 grams of water into oxygen gas and hydrogen gas. How many grams of each gas do you form? So we're going to look at 2 things in this problem. We're going to look at both the oxygen and the hydrogen. So here's our step 1. Here's our equation and it's balanced. So that's my gift to you. So we have water decomposing to hydrogen gas and oxygen gas. Those are diatomics. So they have the 2 subscript. To make it balanced, we need a 2 in front of the water and we need a 2 in front of the hydrogen. So that gives us 4 hydrogens on each side and 2 oxygens on each side. So I want you to go ahead, set up the BCA table, fill it out, and come up with your final answer of grams of hydrogen and grams of oxygen. So let's walk through and check. So step 2 was to set up the BCA table. So here we just set it up in purple. Step 3 was to fill out the table. So if we have 100 grams of water, because that we have to figure out what we start with, 18.01 grams in 1 mole of water, so that's its molar mass. That's a mass to mole conversion. We know that we have 55.55 moles of water. That's what we start with. We originally have no hydrogen and we have no oxygen, so both of those are zeros. We're going to assume that we decompose all of our water, so we end up with 0 moles of water left. The ratio of the water to the hydrogen is 2 to 2 or 1 to 1. So we know that if we lose 5.55 moles of water, we're going to make 5.55 moles of hydrogen gas. The ratio of water to oxygen is 2 to 1. So half as much oxygen is going to be produced. So half of 5.55 is 2.78. So that's down here. 5.55 moles of water, 1 mole of oxygen to every 2 moles of water. So we get 2.78 moles of oxygen gas. So those are our changes. So we lose our 5.55 and we have none left. We gain 5.55 moles of hydrogen gas. So that's how much we have. And we gain 2.78 moles of oxygen gas. So that's how much we have at the end. And finally, our question didn't ask for moles of hydrogen gas and moles of oxygen gas. It asked for grams. So we want grams of O2 and grams of H2, because remember they're diatomics. So we calculated that we had 2.78 moles of oxygen gas. There are 31.998 grams of oxygen to 1 mole of oxygen gas. It's O2, don't forget it's diatomic, so there are 2 oxygens. We end up with 88.95 grams of oxygen gas. If we do hydrogen, we have 5.55 moles of hydrogen gas. There are only 2.02 grams of hydrogen to every 1 mole of hydrogen gas. And we end up with 11.21 grams of hydrogen gas at the end. I want to point out a difference here. We had half as much in terms of moles of oxygen. However, we have way more mass of oxygen than we have mass of hydrogen. It all comes down to the molar mass. That's why you can't convert from grams of something to grams of something else. You have to go through moles. Moles is that equal unit between all of them. Moles is 6.02 times 10 to the 23rd atoms. It's consistent. It doesn't depend on the identity of the substance. However, the molar mass is what makes the difference. So we can't go from grams of something to grams of something else. You have to go grams to moles to grams.